what we're going to do today is we're going to have a look at probably one of the more important things in an assignment in the upcoming assignment 2 implementation. But in week 7 we're going to have a assignment 2 warm-up, which is like a debugging exercise, and some of those debugging exercises also involve knowledge about files and IO and that kind of stuff. So this stuff is going to be important for what you do from this moment to the end of the study period, pretty much. So with that in mind, let's get into it. Okay, if you can't see my slides on the screen right now, click on my name, Paul Miller. But hopefully everyone can see them. Can anyone not see my slides? Nope. Okay. Hoping that means everyone can. Alrighty. So what we're going to do is we're going to start off by having a look at command line arguments. So you know, in C so far, what's the function prototype that we have used for main? What is, if you think about it in terms of the Java idea of a function signature, what is that signature? Yeah. So that void bit, what that means is accept no arguments. But we want to actually accept arguments. So what we're going to do is we're going to actually use a different function prototype. So here we go. We'll use one of these two, either int main int argc char star star argv, or int main int argc comma char star argv square brackets. And what we're going to see is when we get into dynamic memory allocation, that in fact for dynamically allocated memory, these two prototypes are the same thing, even though they're not the same for arrays which are declared on the stack. That is, just give me a sec. So, you know, when we've been looking at for your assignment in cell contents star star is not what we've been using for. That's not valid for passing the board around. We've actually had to use in cell contents, and I'll just use shorthand here, but these are like board width and board height. Yep. That they're not the same thing, but for things like argv they are. So okay. So if you've done, for those of you who've done any kind of shell scripting or whatever, the way that we accept arguments in C will seem very familiar. For example, those who've done bash scripting or something like that. But it's also not all that different, say, for example, to how Java accepts command line arguments. Okay, so we've got these two variables, argc and argv. What do you reckon they have? What's their purpose? Yep, argc is it's the argument count. The v bit is actually short for vector. So the idea is that it's an argument vector. Yeah, so it's an array of strings that we've read in from the command line. Right? So, yeah. So I'll just show you a quick example. Very quick. Let's see if I've got it in shared. Don't really have one there, so what I'll do is args.c and so int main int argc char star argv, right? And then what we might do is something like if argc is less than min args printf error invalid arguments. You are very, very observant there, Sam. Well done. Yep. And alrighty. And otherwise what we'll do is we'll have a count. So here's the thing. What's the number of the first argument in our argv array then? Yeah, because the first argument to the program is the program's name. And the reason why that's possible is there are a range of programs in Unix that behave differently according to what you call them. So I'll give you an example. Actually, in this case, yeah, count equals... Let's do it this way. Instead, we'll actually use a while loop. Count equals 1, right? While argv count So what am I doing here? Well, argv count plus plus. In fact, that won't quite work. I'll do it this way. So what's that going to do? Well, argv count plus plus count. The trick is that at the end of the array, argv array, there is a null pointer. That is NULL, capital letters, pointer. And null is null is 0 cast to avoid pointer. So this is going to jump out when we get to beyond the last argument, right? Does that make sense? Yep. So and let me do this. If strcmp of argv 0 is count or display words, and what I'll do is okay. So let's pull this apart, because this is a very basic program at for displaying command line arguments. So if argc, so let's now hash define some things. Hash define min args as 2. Right? So we have two arguments. First argument is the name of the program and at least one other argument. Right? Then while we've got a string, we'll print it out. And if this program is actually called display words, then we'll print the words as well. So let me just show you that. So what I'm going to do, GCC NC all pedantic args.c minus o count args. Okay, what have I done? Ah, yeah. So I need up the top here hash include string.h. Right. So okay, count args through barbers. Right? 4. So there's a small bug here. What I would do, in fact, is start off with count being 0, and then every time I come across an argument, it'll increment by 1 until we run out of arguments. Rightio. But what I'm now going to do is I'm going to create a link. So I'm going to say, okay, count args, but let's call it count words. Okay, I've made a mistake. Let's just see what's the mistake. Display words. Okay, so we'll do that again. And we'll call it display words. So we'll now display words through barbers. So you see how it actually looks at the first, like what am I being called by, and I'm actually displaying different behavior. If I use display words, then I display the words, but if I just do count words, then I'm just going to print out the count. And the difference really is here where we've compared argv0. So that's the first argument to a program is its name, and after that come the arguments. Any questions about command line arguments? You'll need to use them in assignments coming up. So, yeah, it's a fairly simple concept. So you check that the command line arguments are within the correct range for whatever your application is, and then you print them out, and it's just simply looping through this array. Yeah. Okay. So what we're going to spend the rest of this chat doing is talking about files. And let me just get rid of that little screen there so that things nice and big. So a file is defined in Unix as an array of bytes on disk. That's the only kind of format. It's an array of bytes on disk. And it's external. We're talking about being external because it's not in memory. We can impose additional structure if we wish. And that's kind of a more advanced topic. Well, for example, we might say that I'm expecting this file to be a comma delimited list of integers. So that's additional structure that I've given to a file I'm expecting to read. But the only thing that the C runtime assumes is that it's an array of bytes. And you've got to manipulate that array of bytes in whatever way you see fit. So basically everything in Unix is a file. So you know how up till now with fgetS we've been using standard in, stdin. Yep. Well, that's a file. It's a file which is provided to us, and we can even see it. If I go on, say, the server here, and I cd into /dev, I have all these files. Yeah. And in fact, I can see that I have these files here, standard standard in, and standard out. These are the three files that by default you have access to automatically in C. So you can read from and write to these files without opening them or doing any other work. Okay? Does that make sense so far? Yep. Okay. So this is why I talk about it actually being easier to learn C through on a Unix machine, because the concepts map precisely. Because C was actually developed to reflect Unix concepts by Dennis Ritchie. Okay. So we can access files using C's I/O libraries, and there are operating system specific things. We're not really going to cover the operating system specific things. That's not correct. That's a little bit old. So I'll just remove that. But if you want to get into advanced concepts in C, probably OS stuff is probably somewhere you want to go. The largest C programming project, or in fact the largest software development project ever, is the Linux kernel. It has an amazing amount of something like 3,000 changes to the code base each week or something. It's crazy. So file is a struct. We don't know about the details. We're not worried about the details. It may in fact be different on different systems, but overall the behavior is intended to be the same. Even though the internals of the file structure might be different, there are interfaces we use which are going to be consistent. They're the same in Windows and Unix and on the Mac and every other system where we use Unix. So where we use C, the CIO functions are the same. There are some non-portable functions which you can also use, but we won't be looking at them. Now, functions like fopen, they return a pointer. That is, they return some memory allocated. And so you might get a warning from a memory debugger if you use fopen and you don't use fclose, because part of what fclose does is free the memory which was allocated with fopen. So you want to make sure you call fclose to close any files, but it also frees the memory of the structure that is used to maintain details about the file. So that's why you want to make sure you free it using fclose. Yep, as I've said, I've mentioned that these file pointers you've got access to automatically. It's just part of the resources set up for you by the C runtime when you run a program. Now, before we get into using file input and all this kind of stuff, I wanted to briefly mention how errors are handled in C, because this is, if you're wanting to write professional C code, then you want to know about this. There is a header file called erno.h, which basically, it's a global variable which gets set whenever a system level function is called. So it's not set on functions that you've written, because you don't touch it. But it is set for all the functions that you'll make requests to the system. And typically a lot of functions, what they do is they'll return a null. If they return a pointer, they'll return a null. Or if they return an int, they might return the value EOF, which is -1. And then they set erno, which says what went wrong. And in fact, you can have a bit of a search. I'll just show you that actually. For example, okay, here we go. So there are all these error codes which are actually set, and based on whichever value it is, there's a standard error message which is printed. Just give it a sec for, hang on, I think Jitsi froze for a second there. But yeah, you see you've got these, I'll give you a second to reconnect, but we've got these codes which specify the various error messages which can be set in erno. But I don't remember all these codes. It can be a bit of a pain to kind of go, okay, for this code I'm going to print out this, and for that code I'm going to print out that. So in fact, the C runtime gives us something. And that is P error. And P error, what it does is, according to whatever value erno has right now, it looks up what the error should be, and then prints out the error. So, for example, we'll write a program called openFile. And we might need string.h, so add that while we're at it. Okay, so file star fp equals fopen. Okay, so the first thing we pass in here is the name of the file. So good morning. And I want to open the file for reading. So R is for reading, W is for writing. Now I know this file doesn't exist, so what's going to happen is it's going to fail. FP will be null. And I'll type here, P error, failed to open file. Actually, what I'll do is, open it for reading, yep. And else, okay, so this program just opens a file, tries to open a file for reading, and if it fails, it'll print out an error message, otherwise it'll print out that it succeeded. Where am I? Ah, that's why. So what we'll do is I'll write it in my home directory and call it okay. Yep, cool. TCC, NC, wall, pedantic, okay. So here we go. You see this bit at the end here? That actually came from the system has a global array of strings, which are error messages. So it provides a consistent error message instead of me having to do it. And in fact, if we have a look again at P error, you'll see here we've got this, there's this global sys error list. I've never actually used that array directly, because I just use P error. But yeah, that's pretty cool. So just minimize that. We could use str error. But again, you grab the error node and then you pass it into str error, and it's essentially just doing the work that P error does for you. So I just use P error. Okay. Okay. So yeah, fopen returns a file pointer. So it does some memory allocation, and then it opens up the file and sets everything to the start of the file, if you use read or write, and if you use append, use A, it points to the end of the file. So let's have a look. So there are the different access modes. So read. So we're going to read from the start. Write only mode. Write only mode wipes out whatever was in the file. So if what's there matters to you, maybe you want to be careful about that. And then there's the append mode, which will append to an existing file. So the difference here is the data pointer points to the end, so we're going to add things to the end of the file. So that's the only difference. Okay. But you see here there are two parameters. There's a file that we're going to open, and then there's the access mode. So even though I'm using a single character here, like an R or a W or whatever, it must be a string. So it has to be a string of, you know, say R for read, write, or say append. There are other options, but I never use any except those three for access mode. Because I think that if you open a file in multiple modes, it can actually be a bit confusing. And it allows you to write inconsistent code. So I avoid it. So like for example, we've got this R plus, W plus, A plus. I don't use them because I prefer to use R, W or A for a single mode. Then there are these binary ones, RB, WB, AB. Now, these really only matter if you're programming in Windows. In the Unix environment, all files are binary files because we don't have any additional characters and all this kind of stuff that they have in Windows. So, for example, the carriage return, so the Windows line endings, that is, there's a /r/n at the end of each Windows line, whereas Unix line ending is just /n. That difference in behavior, so it can create problems for consistency. So if you're going to develop in Windows, use the binary format, and then it will work exactly the same as it does in Unix, where, for example, the line ending of each file will be just /n, not /r/n. And particularly if you're submitting stuff, or you're that I'm expecting to be able to work in Unix, you want it to actually behave consistently if you've used Windows to develop. So that's something you need to be aware of. No, there's no difference. No difference using having the B there or not having the B there makes absolutely no difference in the Unix environment, because all I/O in the Unix world is binary I/O in that sense. In the sense that we're just writing bytes. I guess so, yeah. Mostly I don't write software for... It is. So mostly I don't write software for Windows. I don't know much about Windows programming at all, in fact, right? So, but I do know that if you use the binary modes, then that's going to be consistent. So that's probably a good idea, particularly if you're planning to work on Windows. No worries. Now, let's start now talking about functions to do our I/O, right? So we have character input output, and then we have line-based input output. So if you think about F get S, it reads a whole line at a time, right? And so you need to deal with issues around buffering and so on and so forth with each line. Now, you can also use character I/O to read in one character, reading one SHA at a time. Now, one thing to realize though is that all of these functions return an int, and I'll show you this. So if I do man get SHA, right, C get C and get SHA and F get C, they all return an int. Now that int is the character that's being returned. So why do we use an int instead of a char, do you think? Well, part of the reason, it's not really. It is the number that refers to the char, but there's a more important reason, and that's EOF. Right? EOF is in fact an int. It's, you have a line such as, no, that's the null terminator. You'll have a line, say, in send.io.h or somewhere like that, hash define EOF as -1. Okay? Now, a problem here is that if you have something like char ch equals get C sending, right? So get C, and then I do this, if ch. So this has to do with number conversions. So let's step through this. Get C returns an int, but then what's stored in ch? Right? A char representation of -1. And that's not portable. i.e. So as a bit pattern, what could this mean? Could it be 255? Which one? 255 or -1? The truth is, on different systems, they may define a char as being signed or unsigned. So we don't know. For the default char type, right? But what about this? What happens when you have an operation where you have an int and a char? What's the first thing which happens? Before we can do the operation, there's an implicit conversion, right? So you remember, for example, that what's stored in I at the end of line 4? Stop, think. What are 1 and 2? What type are they? Right, so neither one is a floating point number, so there is no type promotion. So it's integer division. So we end up with 0. Correct. So we have sign promotion here, right? But it's not, this is not guaranteed to happen a certain way on all architectures. So if we're starting off with char -1, say, which is, what happens when we convert that to an int, which we have to do when testing this equivalence? We don't know. That's the thing. Is it could become, so whether this is in fact a signed representation or not, it could become so it means the issue is that CH and EOF may never be equal. There may be no way to represent int -1 in a char. Because we're talking about a 8-bit number and say a 32-bit number. Right? So what we do is we store character IO in an int, and only when we no longer need the error information do we assign it to a char. And in fact, what you find is an awful lot of functions which deal with character input use int. So, for example, have a look in so C-type are a range of validation functions that we can use on char, right? But you notice they all take in an int. So the int at the return value is like a bool, 0 or 1. But the int, which is the incoming parameter, is a char. Right? So it's very common to represent a character or a char using an int, using a larger It's just more bits. And all the top bits are all zeroed out. Right? That's a very common way to actually with char data. So that's something to be aware of. And it's this whole issue of EOF being -1. That design issue has caused lots of issues along the way. So here are the kind of functions which you use to read characters or to read chars from input. So get char, read a char from standard in. Get C and F get C. What do you think the difference is between those two, get C and F get C? Look pretty much the same, don't they? Actually, the main difference is that get C is a macro, so it uses hash define for its implementation rather than being an actual function. Would there be any benefit to that? Well, of course there's a benefit to it if it's there, is the reason. But what would the benefit be? It has to do with speed, because you remember with a function call there is overheads of making that function call, right? You have to push each parameter onto the stack, you need to push the return address, you need to jump somewhere else in memory. All of this takes time and space. So what I would do is implement my program using fgetC and then change it in what I distribute to getC. So my deployment would use getC. So maybe even use a hash define to define which one you're currently using. Would be fine. And just like we had them with getting input, we can actually got these with writing input, right? So we have int f put c, so we're going to write this char to the stream. And put c, same except that put c is a macro. Then we've got put char to actually write a char to standard out. Yeah. Okay. So any questions about the kind of char functions? They're all pretty I find that most of the time I don't use them because I tend to use the string functions, but they're there. And what's one of the benefits, do you think, of using these char functions instead of the string ones? What don't we have to know for the shower functions that we do have to know for the string ones. Yeah, we need to know the length. But in both cases, it's still buffered, right? So you're not going to be able to do anything with that input until you reach a new line character anyway. So the input gets buffered and then it's copied so if you use a character function, you're actually copying one character at a time from a buffer in memory. Yeah? You don't need to know the length. Which may mean it's actually more efficient, memory-wise. Okay, so now we've got the string functions. Now, the top one, I probably actually should remove it from the slide because C11 has in fact removed getS from the language. getS is no longer there. So what's the problem with getS? You know, we've got Shasta, getS, and we're going right into this string. What's the problem with that? And how does fgetS solve that problem? Yep, you have no way of knowing how much input is actually going to come in from string. So if we were going to use getS and we wanted to avoid the program crashing, we would have to declare a really big array. And that's really inefficient, so it's not a good idea. It's a wonder to me that getS ever made it into the standard. But thankfully, pretty much the ruling is, yeah, don't use it. Bad idea. Okay. So, is anyone at this point unsure about how to use fgetS? I think this is really important because you're going to have to use it correctly in your assignment. So speak now and we can talk about it, or I'll move on because we've dealt with it a lot in the previous weeks. And for good reason, because often people struggle with it. So don't forget things like your string tokenization and conversion kind of stuff, which we talked about in week 3. And I've got examples that use that kind of stuff as well. So we have a look at in shared and it'll be yeah. So if you need to brush up on using Stratok, this is probably a good example to go with. And so we have a look in, so we look in load. Further down, we've actually got the actual functions to read into the file. So we use strtoc to grab the next token, read in the each token, copy it in, and then copy the data into the array and move on to the next one. That's a classic example of using strtoc. Anyone struggling with strtoc? Okay. Hopefully that's will be a good example for you for if you're struggling at all with it. Okay. So what we've got so far, the material I've discussed so far, is the material you really need to come to terms with for the assignments. Having said that, it is really quite common in CIO to actually need to jump around in the file to various places in the file, and for that we use these functions fseek and ftell. So absolutely, for tokenizing your moves and that kind of stuff, you'll need to use strtoc. And in fact, like the way I've constructed the moves was, in fact, it's meant to be an assessment around using strtoc. Okay. So here we have fseek, where we pass in the actual file pointer. Where do we want to jump to in the file, which is a long, and int from. Now from can in fact be seek set. So this many bytes from the beginning of the file. Seek current, so this many bytes offset from where I currently am. And seek end. This many bytes offset from the end. So for example here, I'm jumping to 5 bytes before the end of the file. -5 from seek end. Whereas if I wanted to move backwards by 1 byte from the current location, is I would actually fseek stream -1. And let me just have a look at what these fellows return. So man fseek. Okay. So they return 0 when the seek was successful. and -1 if they failed, and then they set error. So you probably want to use something like p-error to handle those errors. And then we have ftell. So let's have a look at ftell. So ftell obtains the current value of the file position. Why was it, do you think, that back when we all had 32-bit operating systems, we could only have a 4 GB file? That was the biggest file we could create. Something, in fact, in these data types gives you a hint to the problem. Well, on a 32-bit system, a long was only 32 bits. So, if we have 2 to the power of 32, that's why our limit on file size was 4 GB, because we can only refer to 4 billion bytes. Whereas these days we have 64-bit files, 1.8 with 20 zeros on the end. It's ridiculously huge. It's exabyte sized files we can theoretically store, or we can at least refer to with, because long is now a 64-bit number. That means that our files can be much bigger. Okay, does that make sense? Okay. Now, this is something which people struggle with. It won't be on the exam, but it is something that is important to understand, particularly if you're going to do any kind of any decent kind of programming beyond this course. And for example, have any of you used serialization in Java? This is the idea that we can write out entire data structures in one go. Now, why is that awesome, do you think? I've got this big array, and I just say, hey, this is the array, this is how big it is, write it. As opposed to actually having to say, okay, write out this line of the array, then this line of the array. having to actually build it up. It is, but you actually, it's not human readable because it's all in binary. Basically what you're doing is you're writing out the contents of memory to disk. So there's lots of issues, like for example, if the structure that you're using has pointers, that's useless. Why is that useless? Pointer values are actually initialized on each run of a program, and they're different each time. So saving out pointer values is pointless. Anyway, it's there is one of the exercises for the materials for this week actually has an example using binary I/O, and probably something to point out here is we got this void pointer. What on earth is that? What's a void pointer? Correct. It's a pointer to any memory. We don't care what it is, but then we don't know how big each element is. So this is an example of a function written to take any pointer in, but then it says I need to provide the size of each element and how many. The size of each element is what's in a data type. You know, like an int is 4 bytes and that kind of stuff. Here it doesn't know, so we have to tell it. Okay. So I'll just show you a very quick example of that using convert. Convert.c. Okay. So what we're doing here is we open up a file, we load in the data. So let's have a look at that load. So we read in each line using fgetS. And then what we're going to do is we make a copy of the line because Stratok actually modifies the string. So we tokenize the line, copy the data in to our array, like so. So that's the load. And yes, a void pointer can be a pointer to any memory address whatsoever. So up here again, after we do the load, let's have a look at save, because that's where we use okay. So we use fwrite to write out our data. And so what I'm doing here is a technique called marshalling, which is often used when I'm going to write out binary data. So this first thing, what's num entries? What's this variable over here, num entries? Yeah, the number of phone book entries in the phone book. So I say, okay, I'm going to write out the number of entries. How many bytes to write out? The size of a size T, so one size T to the output stream. So if that thing is that it tells you how many items were written. So if one item is written, then that was successful. Then we have this second F write. So we're going to write out the phone book. And we're going to write out the size, that each entry is a size of a struct phone entry. Because that's each element of the array is a struct phone entry. How many entries? Well, the number of entries. And so when I read this data in, there's two things that you would need to read in. You would need to firstly read in the number of entries. So you know how much extra data to read after that. So it would tell you, okay, so if there were 5 entries in the phone book, then you actually would be reading in 5 times the size of a struct phone entry. Does that make sense? And keep in mind with this is reading and writing actually what's in memory. There's no conversion when it goes to disk, it's exactly what's in memory. Can you think of a problem this might create? There's something that is commonly referred to as Indianness. Anyone heard of that? Indianness? Yeah. So it's which byte gets written first? It does. They're Lilliputians. But anyway. But it means when you got a number in memory, we could represent the first byte as the lowest entry, or we could represent the first byte as the highest value byte. And according to which byte comes first, we have this idea of Indianness. Unfortunately, Intel went one way and the rest of the world went another way. But guess what? Intel has become the most popular in the consumer market, which means we have to write bytes differently for low-end consumer machines versus server machines. So it means that writing bytes out to disk like this is not portable, but there's ways to get around that. Okay? So the really important stuff, in my view, coming out of this, is to make sure you understand command line arguments. It's a really important thing to take away. That you make sure you've understood fgetS, opening and closing of files, and fgetS. Yeah? And because you'll need all of that absolutely for the assignment 2 warm-up and assignment 2 implementation. Any questions? Okay. I really encourage you to work on the exercises for this week, and so I might see a few of you tomorrow. But also, good luck with your assignment. At this point, you should be getting stuck right into it.